All right. So we left off talking about the binomial distribution. So we'll kind of pick up with that. Work through that, do some stuff in Excel. So the last part of the Excel assignment we'll actually go over today. After today, you should have everything you need to get through that. And then we'll just have one more thing to cover on Monday. I'll mention that later on. And there's a couple questions on the Connect that's concerned with that, but you should be able to work through the vast majority of that Connect assignment as well. Okay. So we had this binomial equation last class. Let's see if I can do this from memory. Which, if we had an example where we had a success failure, right? We're looking for, did something happen or did it not? Right? Did it come up, coin flip come up heads or did it come up tails? And we wanted to find the probability of a different number of successes out of a certain number of trials. We could use this probably, binomial distribution equation. So instead of an easy coin flip example, let's think about something maybe a little more practical. Let's say I know that 30% of US adults have a 4-year college degree. And I then want to know, okay, out of 5 randomly selected adults, what's the probability that exactly 3 have a degree? So the 3 components that we always need to identify are our number of trials. Well, here I'm looking at 5 people. What am I interested in finding the probability of? That exactly 3 of them have a degree. And then the underlying probability of success that any one person has a degree. If I was just looking at one person, well, that's our 0.3, right? That 30% of US adults have a degree. From here, it's just a matter of getting our values plugged in, right? So everywhere where I see an N, I'll put in 5. Everywhere I see an X, I'll put in a 3. And then everywhere where I see this underlying probability of success P, I'll put in 0.3. Okay. So I've just taken that general form of the equation, have that in that formula sheet going into the exam, and just substituting in this problem what my 3 components are. Okay. So if you haven't found your factorial button on your calculator yet, for an example like this, it doesn't really matter. I mean, I think if we write this out, we can kind of think about, well, I could write this out, and so 5 minus 3 is 2. I could probably get this entered into my calculator without having to use that factorial button. If I'm dealing with something larger, it's probably a little bit, time consuming, to enter it in this way. So like I said, good thing to kind of try to find that factorial button, because we'll also be using it in what we talk about on Monday, right? And then from there, right, just do the math in your head that you can do, kind of simplify this. Why carry all these parentheses and stuff when hopefully I can do 5 minus 3 in my head, right? Any questions on that? So all I did was kind of take that general form of the equation, we then plug in our kind of values, and then end up with a probability that we see exactly 3 of the 5 people have a degree. Any questions on this before we keep moving here? So I also mentioned something else last class, which is how do we find the mean or the expected value of these binomial distributions? Well, it's kind of easier to think about, like, let's say I had 10 people, right? What's the average number of people I would see have a college degree out of 10? That underlying probability of success is 0.3, or 30% of people have a degree. Out of 10, the most common number of people I would see have a degree would be what? 3, right? And what we're doing kind of intuitively there, all I'm doing is taking the number of trials, multiplying it by the probability of success. We don't have 10 people here. We only have 5. So instead of 3, I get kind of the expected value, or the mean is 1.5. Okay. Well, this is discrete, right? So if I'm thinking about these different outcomes, that mean of 1.5, I'll actually never see that when I run these experiments, right? Or when I randomly sample these 5 people. But that tells me that would be kind of the expected value. Then I'll just look at the integers on either side, and I know those will be the 2 most likely outcomes. So here, seeing 1 of the 5 people or 2 of the 5 people have a degree, those should be the most likely outcomes or have the highest probability. Okay? As I move further from that point, I just get that the probability of a higher number of successes or a lower number of successes, that should be declining. Okay. So we just found the probability that 3 is 0.13. So I would then know the probability I only see 2 of the 5 closer to that mean, that probability should be a little bit higher. Okay. Any questions over any of these ideas before we keep moving here? So I think it's important to kind of get a little bit of practice kind of working through these, make sure we troubleshoot, figure out any problems we're having, kind of getting these into our calculator. Order of operations can sometimes be a little bit tricky, so just a little bit of practice with this lets me see how you guys are doing. Let's say instead we have the same setup, but instead of finding the probability that 3 of the 5 people have a degree, I want to know what's the probability that 4 out of the 5 people have a degree. Okay. So I'll give you guys a little bit of time to work on this. Like I said, feel free to talk to people around you, work together, and we'll kind of come together and talk about it. So the general form of the equation, everywhere I had 5, I had 10, 3 was x, and then p was 0.3. That kind of helps you. Remember our factorials, 5 factorials is 5 times 4 times 3 times 2 times 1.
What would the 4 be representing in this one?
Here?
Like, I guess, yeah, it's like,
Oh, I was just making the point before, we were finding the probability that 3 of the 5 people have a degree. Now we want to know what's the probability that 4 of the 5. So we're interested in the number of successes. Now instead of 3, we're interested in the number of successes. Yeah, 4. See the vast majority of people fine. So I'll be kind. If you guys are putting an effort, then I'll generally reward it. So we have the exact same scenario that we had before. Whatever where we have a 3, we're now going to have 4, right? Because we're no longer looking for the probability of 3 successes. We want to know what's the probability that I have 4 successes. So if I wrote this out in the context of my example, it's going to look something like this. Right? Now from here, one thing I could do to make my life easier, and I don't have to do this, I can enter this into my calculator and it can handle these low number factorials, but we'll look at an example in a second where we can't. So 5 minus 4 is just 1 factorial. Multiplying anything by 1 doesn't really change anything. If I wanted to, I can kind of ignore that. Everything here is going to cancel. This entire fraction It's just 5. All right. I then have what? 0.3, oh, I forgot, to the 4th, right? So times 0.3 to the 4th. And then here, hopefully I can simplify this, 0.7 to the first power. Anytime I take something to its the power of 1, it's just the number itself. So if I wanted to here, I could just put in 0.7. So it simplifies down to this, right? If I kind of write this out. And now I can type this all into my calculator and use parentheses, whatever, like that's fine, right? But sometimes simplifying it kind of makes it a little bit easier than when you're kind of generating integer calculator. Now, I could have gone through and done this, right? But which of these has to be, based off of the previous problem that we did, which of these has to be the correct answer? If I found the probability that 3 is 0.13, what do I know has to be true about the probability of 4?
It's less.
It's going to be lower, right? As I move further from that mean or that expected value, the probabilities decline. So the only one up here that makes any sense, right, is 0.028. It's the only thing that's less than that 0.13. Right? So it's just still open. You can always change your answer. So hopefully everybody gets this one correct. All right. I'm going to close it out here. I'm also getting worried about the number of people in class 1 week prior to an exam, but I'll keep those worried to myself. So, and you guys don't care about it because you're here. So we've got everything plugged in. I'm just happy to get this into our calculator. Like I said, we can simplify this, right? We end up getting about 0.028. Okay. Any questions over anything, or kind of running any problems as we're working on this? Any questions about them? All right. So let's go to a slightly different type of problem. So let's say instead, I don't want the probability of exactly one number of successes, but here I've got what's the probability that at least 3 out of the 5, so greater than or equal to 3, right? What's the probability I see at least 3 people have a college degree, or that X is greater than or equal to greater than or equal to 3? Well, it ends up being true because these are mutually exclusive events. If I look at these 5 people, either exactly 0 of them will have a degree, either exactly 1 of them have a degree, exactly 2 of the 5. These are mutually exclusive events. I'm going to see just one of these number of successes. So we said if that's the case, and I want the probability of this or this or this, the union, if they're mutually exclusive, I'm not double counting anything. I'll just add up the probability of every single possible outcome that fits that criteria, right? All the numbers of successes that I could see that are greater than or equal to 3. So the very first one would be probability X is equal to 3. Add to that, the probability is equal to 4, and then add to that, the probability is equal to 5. Well, why do we stop at 5? I've got 5 people I'm looking at. I can't see 6 of them have a college degree, right? I stop at that maximum number of trials, okay? So now I use that binomial equation 3 different times. N and P are always the same, but I'm looking for different X values, right? Different number, the probability of different numbers of successes, okay? So I'll use this 3 times. Well, for our, lucky for us, right? We already had found these in previous problem, right? Probably X is equal to 3 and 4. So now it's just a matter of finding probably X is equal to 5, adding them all up, right? So probably X is equal to 5, pretty small, right? As I'm moving further from that mean or that expected value of 1.5, the probabilities are declining. By the time I get to all 5, right, it's pretty low. Okay? Now I want to point something out about that probability though. So let's say I want the probability X is equal to 5, right? So we get n factorial, x factorial, n minus x factorial, probability of success to the x, 1 minus the probability of success to the n minus x, right? And I write this out. So what also should be true, except for these binomials, like these events are independent, right? Coin flips are independent from each other. These people are these people getting a degree is independent from the other person getting a degree. And so, or having a degree, I should say, not getting one. So it should boil down to just like when we were talking about like the roulette table, right? Well, if I want to know, are all of these trial successes, right? What's the probability that out of 26 spins, I saw black every single time? We said it was just take the underlying probability of success on any one spin, 0.5, multiply by the probability of success in the second, so times 0.5, times 0.5, all the way to 26 times, right? or we said 0.5 to the 26th power. Same idea here. If these are independent events, these people having a degree are independent events, well, then the probability that all 5 of them have a college degree should just be 0.3 times 0.3 times 0.3 5 times. Right? Well, notice if we simplify this equation down, 5 factorial divided by 5 factorial cancels. 5 minus 5 is 0. We have this unique thing I mentioned last class, which is just 0 factorial is equal to 1. So this entire fraction is just 1. I can ignore it, right? Multiplying by 1 doesn't change anything. Here I've got, so now I've just got, I guess here I've got a 1, but I can kind of ignore it. So do the math in my head that I can do, 0.7 to the 0. Anything to the 0 power is just 1, so that cancels. Really all I'm left with, if I want to know what's the probability that all of them are successes, yeah, I can plug everything into my binomial equation, but it'll always simplify down to just being that probability of success, however many trials I have, because I'm looking for all of them being successes there, I would have n and x being the same value. So when you're wanting to know, what's the probability that all of them are successes, a lot of stuff simplifies and this actually becomes a little bit easier. Any questions on this idea before we keep going here? I'm gonna throw some other stuff in the mix. That idea. All right, so we add those all up, we get about 0.162. We've already talked about the mean. Another thing we can talk about is the variance. This isn't overly interesting or intuitive. The mean was pretty intuitive. This is the idea. If I flip a coin 100 times, it probably comes up. What are the average number of successes I'll see? Well, usually 50 out of 100 would be the most common, right? And then further from that in either direction, the probability decline. Not quite as intuitive the variance, but we have the mathematical proof that shows as long as we have this 1-0 variable, 1-0 outcome, that will always we can simplify what the variance will be down to n times p times 1 minus p, right? You think about really what we'd be doing there, it's kind of complex, but calculate the variance, I'd be looking at every single x value's deviation from the mean. The mean is n times p, we're squaring that, multiplying that by the probability that we see x be equal to whatever the outcome is. This is the binomial distribution function. We plug that in and it just works out. You can prove that it always simplifies down to this equation, right? It's pretty easy. N times p times 1 minus p. And then as always, if we want the standard deviation, we just take the square root, right? So we've already talked about the mean in this example, but just to kind of give an idea, right? If I calculate the mean here, I would be n times p, so 5 times 0.3 was 1.5. And if I wanted the variance, well, that was n times p times 1 minus p. So 5 times 0.3 times 1 minus p would be 0.7, right? This shouldn't be too wild. If you have this function in front of you on the example I asked you for the mean and variance of a binomial distribution, hopefully be pretty easy, right? I have that formula in front of you. These are some easier ones to kind of plug things in and you don't really have issues with orders of operations or anything like that. Any questions on that for you? All right, so I'm going to hammer this point home a little bit. I stole this because I like this some stuff in the book, so I stole this from them. So, kind of give a nice visual of what these binomial distributions are going to look like. But we're finding we have all these different successes. We can find the probabilities. We could graph them out, right? Kind of plot them as a bar graph. So, if I have, let's say, 5 trials and I have a relatively low probability of success, 0.1, my mean there, n times p, would be 0.5. So 0 and 1 should be the most likely outcomes. Notice even in this example, we're not saying they have the same likelihood of occurring, right? Here you can see the probability of seeing 0 out of 5 is much higher than the probability of seeing 1 out of 5 successes. But those are the 2 most likely outcomes. Okay? And then as we move from that mean further away, the probability of seeing higher number of successes is closer and closer to 0. If we have this relatively low probability of success, we've got this kind of right skewed distribution. If I then think about having a really high probability of success, 0.9, well there, n times p would be 4.5 would be my mean. So 4 and 5 will be the most likely outcomes. And then as I move away further from that mean, right, the probability of seeing a lower number of successes starts to get closer and closer to 0. And if I have a high probability with my binomial distribution, I end up with this kind of left skewed distribution. Okay? And then what if I have exactly the probability of 0.5? Well, here my mean would be what? 5 times 0.5 is 2.5. 2 and 3 would be the most likely outcomes. And as I move in either direction, those number of successes probabilities start to decline, getting closer and closer to 0. But you'll notice when the probability is 0.5, I got a nice symmetric distribution. Kind of shows better if I look at a sample size of 50, and I have the probability success of 0.5, so their most common number of successes I would see would be 25. That's the most likely outcome. And then as I move in either direction, that probably gets closer and closer to 0. That kind of makes sense. If I'm flipping a coin 50 times, probably I see 0 of them come up heads, or the probability I see all 50 of them come up heads should be really, really low, right? Really close to 0. Any questions on this idea? So we'll go through this here real quick. And this will make a little more sense, I think, on Monday. So we have binomial distributions. That's a very specific type of discrete random variable. We'll also have something called the Poisson distribution, which has kind of its own probability mass function, right? It'll use the factorial. And once we talk about the Poisson, I think it'll be a little bit easier to differentiate cases where we apply the binomial versus where we apply the Poisson. But I'll kind of introduce the idea here today. So we're thinking about scenarios where we could use the binomial distribution. We're looking for which one doesn't, right? So 3 of these will. So the first one, we're going to calculate the number of expected coin flips that come up heads in 123 flips. Hopefully this one's, we know is, I've used this example already several times, right? We have success, failure, heads or tails. The underlying probability of success in any one trial, we know, is 0.5. I've got N, I've got P, or sorry, I've got probability of success, I've got success, failure. I know the number of trials I've got is 123 flips, and I could then find the different probabilities of seeing 60 of them come up heads or 73 of them, right? This is a good example where we use the binomial. What about 5 out of 20 patients getting sick from an antibiotic? Well, if we know that there's just some underlying, based off of some previous data, some underlying probability that if someone takes this drug, here's the likelihood they'll have an adverse reaction, right? We have our underlying probability of success. We've got X being 5 or greater, right? At least 5. And then we have our number of trials being 20, right? So 5 out of 20 people getting sick, we know the underlying probability of any one person getting sick, we could use the binomial here as well. Calculating the probability that out of 5 customers, exactly 3 make a purchase. Well, if we looked at like the data, right? A lot of these stores that have got video cameras, they can figure out how many people are coming in and out and how many people actually bought something. So you would know that if I chose someone at random, here's the probability they purchase something if they come to my store. So I've got that underlying probability of success. I want to know what's the probability that exactly 3 of 5 customers buy something, right? These random 5 customers. So I've got a cap, the number of trials is 5, and the number of successes I'm interested in finding a probability is 3. This is a good case where we can use the binomial. The one that doesn't make sense is going to be C, right? And so we'll think about why. Let's say, what's the probability that the Muncie Airport, their air traffic controllers make 3 errors per week, right? Well, I might know that on any one landing, what the probability they make a mistake is, right? So I could maybe have this underlying probability of success. I'm interested in what's the probability they make 3 errors. Here it's kind of weird, but errors are my successes, right? But how many errors total? Like, what would be the highest number of errors they could make? I don't know. I mean, I guess maybe in these examples, sometimes we can be like, take the time and figure out how many landings could possibly happen in a week, but it's going to change week to week. And so we don't really know what that cap is. We don't know what that maximum number of successes we could see on, right? If we're looking over like a time interval, here we're looking over a week, right? As opposed to looking at 100 landings, right? If this instead had been phrased, what's the probability to make 3 errors in the next 100 landings? Well, then we actually have a cap. We would treat like that like a binomial. If we have this kind of open-ended time interval, those are going to be scenarios where we actually apply the Poisson distribution. Like I said, we'll kind of look at that on Monday, so it'll make a little bit more sense and how we would tackle a problem like this, where we don't have a cap. We don't have a maximum number of successes that we can see. Questions? Keep going here. We got one more thing, and then I want to do a little bit of work in Excel. So let's say I had an example, and I don't know, let's do N, X, P, We'll make this one kind of hard. Let's do 100. 2. Then I don't know, 0.05 or something like that. So I've got this scenario, and let's say I wanted to know what's the probability that I see at least 2 of these 100, whatever the example is, maybe this is, I think the one I use in Excel, I'll be doing like homes foreclosed upon or something like that. So what's the probability that we see more than, greater than or equal to 2 homes foreclosed upon if I'm selecting 100 of them at random, right? Well, if I think about how do I write this out, this is the probability that X is equal to 2 plus the probability X is equal to 3 plus the probability X is equal to 4 all the way up to 100. It seems a little suspect, right? Like I got to use this binomial equation, 98 different times. If I asked you to do this problem in the exam, there's no way you would have enough time, right? But I could ask you this problem in the exam, because if we combine some of the other rules that we've talked about, if instead I think of this as event A, it's another way that I can find the probability of A.
1 minus A.
Yeah, 1 minus A complement, right? Right? So here, excuse me, if A is greater than or equal to 2, the complement of that is being just less than 2, right? Well, what are the only outcomes that fit this criteria? I have a discrete random variable, so the very first number of successes that would kind of happen here would be what? X being equal to 1, right? That's the first outcome that's less than 2. That's discrete, right? I can't see decimals. And then also, I could see that I have 0 successes. Well, now I only have to use that binomial equation 2 times and then subtract them from 1. Right? So sometimes when you have things that look like you're thinking about, it seems like I shouldn't have to be using this binomial equation this many times for this problem. Probably a good indicator that you could use its complement and make it a lot easier. Right? Or sorry, I should say 1 minus its complement. Any questions on that idea? Something changed or okay with this? Okay. So I'll keep this in here. I think I had like a millionaire example, but I'm gonna change it to be an example I used earlier because I kind of like it a little bit better. So you've got an example in the slides, and then I'll end up posting this. I've just got Excel open. I'll end up posting this file after class, all the work that I do. But we can kind of think about using this binomial distribution function. So this will be the thing that's kind of applicable to the very last question on your Excel assignment. So I'm just going to type in some headings here. So I've got my number of trials, the number of successes I'm interested in finding the probability of, and my underlying probability of success in any one trial. So let's say I'm looking at 100 homes in Detroit. And I know that if I look at the data, the probability that if I select a home at random in Detroit, that they default on their mortgage is 0.047, right? So I've got my underlying probability of success, and then maybe I'm interested in finding the probability that exactly 10, of these homes get foreclosed upon. Right? So what I'm really looking for there is, what's the probability that X, this number of homes that gets foreclosed upon, right, is exactly equal to 10 of these 100. Well, we can plug everything into our binomial distribution equation, or Excel has that equation built into it, right? So it's got this built-in function binom.dist, right? All I have to tell it are my 3 things that I would use if I was doing this by hand. So the very first thing is our number of successes we're interested in finding the probability of, which is just 10, right? So if we're writing this out, first thing we want is X. The next thing we want, it says, is the number of trials. So put a comma. Here, our number of trials is over here. The next thing it wants is that underlying probability of success in any one trial. So any one home that I select has a probability of being foreclosed of 0.047. And then comma, this last thing, and the fourth thing that it needs is we're going to use a 0. All right. So the reason why we're using 0 is because this last thing says, okay, and it says you can type in true or false. Anytime you have a function in Excel where you can do that, 1 and 0, 1 is true, 0 is false. So if I tell it 0, that says don't make it cumulative. If I tell it 1, that says, yeah, find me the cumulative probability, which in this case would be finding the probability that x is equal to 10 plus the probability x is equal to 9 plus the probability is equal to 8, right? And adding down to 0, right? Making it cumulative, starting at this x value and adding up the probabilities of every possible outcome below it as well. We don't want to do that. We just want, the probability of exactly 10. So we're going to put a 0 in there. All right. Now, if I hit enter, I can get that probability pretty quickly, right? And I could start to play around with this, right? I could like, oh, it's a probability I see exactly 20 of them or 13 or whatever number I'm interested in, right? And all I would have to do is go back here and play around with this probability or this number of successes and get its corresponding probability. Questions on that before we keep going? What do we do next here? Let's do. So if I put a 0 in, just kind of show you this is a nice little trick. If I get that black plus sign down in the bottom right corner and I right click and drag this down, it'll give me these options. If I go to fill series, it'll just automatically update them by 1, right? So, or I guess not update them, but kind of increase the values by 1. So I want to go all the way up to 10. So I've got kind of this column now. Right? What I'm going to do, and you can also, like, if you do that, notice it, you go down to series, it gives you other options. Like you can do jumps of 10 or 100 or whatever you want. It's kind of a nice little feature they've got. So here are our different X values. And we can find the probability of these different number of successes using that binomial distribution function, right? So binom.dist. Now I'm interested in finding the probability of 0 successes, comma, my number of trials is 100, comma, underlying probability of success in any one trial, 0.047, and comma, 0, I don't want it to be cumulative. If I do this and I copy this down, notice my cell reference will keep updating to give me the probability of different numbers of successes. Right? However, I'm always going to have the same number of trials and the same underlying probability of success in any one trial. So I'm going to look at those cell references and say, okay, when I copy this down, I never want these to change, right? So I'm going to freeze those. But now when I copy this down, the next line I would have the probability not of seeing 0 of the 100 homes foreclosed upon, but 1 of the 100, and then 2 of the 100, so on and so forth. So if I do this, another nice shortcut, if I've got like a column of data or a column of numbers like this, if I double left click, it copies that down automatically for me down to the very last cell next to it that had a value in it. Okay. So I might be interested in something like, what's the probability x is less than or equal to 10, right? Well, I know I would have to take the probability x is equal to 10 plus the probability is equal to 9 plus 8 plus 7 all the way down to 0. Well, coincidentally enough, that's what I have over here. I could just use that sum function, add all those probabilities together. Okay. Now I can do it that way, but what I could also do is use that binomial distribution function. And if I tell it I want to find the probability of 10 or fewer successes or make it cumulative. So there, what would I do? I would say, okay, what's the probability that, and I'll just type 10 in here because I might not, well, I guess I could reference it over here. So start at 10. I've got 100 trials, comma, underlying probability of success is 0.047. The only difference now, because I want it to be cumulative, not just find the probability of exactly 10, but of 10 or less, right? Instead of a 0 here, I'm going to put a 1. Okay. Now, when I hit enter, hopefully I get the same thing as when I found each probability individually and added them all up. Sure enough, I get the same value, right? And, I don't have to like create this whole table. I can kind of find it very quick. Questions on that? Now, the one thing you need to be careful of, let's say instead I wanted the probability that it was just less than 10, right? Well, this probability is the probability that it's 10 or less. So what value would I actually need to use if I wanted the probability of being strictly less than 10? Yeah, the next possible outcome, which is discrete. So the next thing I could see, I should actually be putting a 9 in there, right? And I'll actually, well, here. Copy this. Oh. Copy. Paste, so I have the same thing. So this was our kind of check on that. If I wanted it to be strictly less than 10, this is where we said we would have to, instead of using 10, use that value of 9. I'm just putting this so that when I post this, you gotta have both of those to look at, and you're like, wait, the change things around. So we can use this cumulative option to help us find these different ranges of probabilities, but we have to kind of be careful with that equality. Okay. What if instead I'm gonna do a trickier one here. I wanted the probability that X is greater than, oops, I forgot X in the probability that this random variable X, this number of homes that we see foreclosed upon, is greater than 5. Well, I can't use that cumulative option because that would take the probability of 5 and add down to 0. I need to go in the other direction. Unfortunately, there's no option in that built-in function where you can look at the probability of being above a certain value, right? I don't think it would be that hard for them to program that in there, but it's not, right? So what can we do? If this is my event A, right, I know that I can rewrite that as 1 minus the complement. Right? So this was a complement here. So 1 minus the probability X is less than or equal to 5. Well, I can use that binomial equation to find this pretty quickly, right? It's just that cumulative option. So I can use that binom.dist. I tell it I want what, 5 successes, comma, out of 100 trials, comma, underlying probability of success in any one trial, 0.047, comma, I want it to be cumulative, right? Now this would give me the probability that X is less than or equal to 5, but I still then need to subtract it from 1. So I could find this and then do that in a different cell, or you don't have to separate everything up. I do it a lot of times just to kind of show you the steps. You can do everything in one cell, right? So it'll basically find the probability that X is equal to 5 plus 4 plus 3 plus 2 plus 1 plus 0. Whatever that number is, it then subtracts it from 1, and then it'll show you that in the cell. So you can kind of do multiple things in the cell at one time, right? Use multiple built-in functions, use math and a built-in function, all different alternate combinations. Any questions on this before we keep moving here? All right, so I think if there's anything else I wanted to point out here. Oh, I know what I want to point out. So this is I don't know, I just want to, this might seem like I was just exercise and just, I don't know, figuring out this probably binomial, but what's the actual application? So this, you know, you can imagine, like, if I'm got some scenario where I'm looking for a company, like the bank here is like, well, look, yeah, we've got these 100 mortgages that we're holding. If 10 or more of them default, or I guess here more than 5 of them default, we're in trouble, right? So what's the probability that more than 5 of them default? It's high as 33%. I might be concerned, right? I might want to make sure that I have a backup plan that if more than 5 of these homes foreclose is going to put my company in a bind. Like, that's going to be a problem, right? If the probability is as high as 0.33 or 33% chance of that occurring, right? You could also think about, you know, if I'm a store or something, I'm thinking about, you know, I've got 100 customers a day. What's the probability of seeing a different number of sales then? Right? I know the probability that any one person buys something from historical data is this. I can figure out, okay, tomorrow, what's the probability that I sell 10 of items, or 10 people buy something out of 100, or 15 of them, right? Well, I can set these schedules up, right? And then as things change, I can just update it. So think about like the home being foreclosed upon with the bank example. Maybe they're doing this year by year. And in this year, the percent or the probability or the portion of homes that have foreclosed has gone up, right? I've had new data, I can update that probability. If I have my table set up like this and I hit enter, notice everywhere where I was kind of referencing that underlying probability of success, if that thing changed, everything else changed as well, right? So now I've got my updated probability that I see exactly 5 homes foreclosed, or exactly 6, or greater than 5 of these homes foreclosed upon, right? So now, so it's pretty, 50-50 chance whether or not I see, I'm in this, bad scenario where I have more than 5 of my homes being foreclosed upon, and I've got these mortgages that I'm no longer able receiving money for. So this is pretty applicable to like a lot of different sales jobs. It's gonna be applicable to anything where I'm interested in if something's happening or not. And I'm looking at a certain number of people or a certain number of products, like this could be, if I'm looking at an assembly line, right? So this is like, would be more like a management, maybe industrial engineer, become an industrial manager, right? You might be overseeing something, you say, hey, look, we're creating 1,000 products today. We know that our defect rate is 3, right? So, or sorry, our defect rate is like 0.03. So what's the probability of these 1,000 that 100 of them aren't good, right? Because if we have 100 or more of them not be good, we can't meet our production, like our sales, right? It's so, what am I thinking about? Like, so we can't meet like, why am I blanking on this word? Orders that have come in. Sorry, I don't know why I couldn't grab that word. But yeah, this is like very applicable to kind of scenarios like that. Hopefully it's not too bad. So this should be all you need for that last part of the Excel assignment. Be careful when we're thinking about kind of being in between two values. So I could do that as well. So like, let's say, what's the probability that X is greater than 5? Whoops. Oh no. Let's say X is greater than 5, but less than 10, right? So what I could do is find a probability of every possible outcome that meets that criteria. So the probability that X is equal to 6 plus 7 plus 8 plus 9. I use that binomial distribution function, not making it cumulative 4 different times. Or I could think about really what this is the probability that X is less than 10 minus the probability X is less than or equal to 5, right? Because if I take every single outcome in this range, right, if X is less than 10, that's the probability that X is equal to 9, plus 8, plus 7, plus 6, plus all the way down to 0. This probability would just be the probability that it's equal to 5 plus 4 plus all the way down to 0. So when I subtract that out, all I'm left with there would be the probability that X is in between those two values. So how can I do this in Excel? I can kind of break this down. Well, use that binomial distribution function, right? What's the first value I had? So I wanted to know, was it less than 10? The problem is, if I use it this way, comma, number of trials, comma, probability of success, and I make it cumulative, right? So that it's adding up the probabilities all that are less than 10, but I didn't want less than or equal to. So instead of 10, what I should be using there is the first, outcome that would meet that criteria, right? X being less than 10, first outcome that meets that criteria is that X is equal to 9. So now this function will give me the probability X is equal to 9, plus 8, 7, plus 6, all the way down to 0. Well, I want to subtract out from that anything that is 5 or less. So what I can do there is on the same cell, use another binomial distribution equation where I take the probability X is equal to 5 all the way down to 0, right? Or making it cumulative. So here, number of successes, comma, underlying probability of success. It's just that now I'm going to use that cumulative option. Okay? So I've got, this should give me the probability that X is less than 10, subtract the probability X is less than or equal to 5, which should give me that original probability I wanted, which was that X was in between 10 and 5. Okay. Questions on that idea? So you have to be a little bit careful with your equalities, right? If I've got like a strictly less than or strictly greater than, I have to think about, well, the value I'm using in my binomial distribution function is actually, the first possible outcome that meets that criteria. So if I have strictly less than 10, first outcome that meets that criteria would be 9. Questions on this idea? I want to do one more thing to hopefully, I think, will help of why this works. And I'll let you guys get out of here. So let's say, thinking about my example here. I don't know, there's these different probabilities. So what we're doing is thinking about if I want to know the probability it's in between 5 and 10, well, that's really taking the probability of 9 and everything below it, adding them all up, right? But I only want the outcomes of 6, 7, 8, and 9, right? Because I also want it to be greater than 5. So what I need to do is I need to then subtract out adding up all these probabilities. Well, notice we're always going all the way down to 0. So these are just cumulative. We could just find cumulative probabilities, right? So adding up every outcome that's less than 5, subtracting that from everything that's less than or equal to 9 would give us that probability that we wanted of being between 10 and 5. Yeah. Binom range. Yeah, I don't expect you to know how to use that. It gets a little bit tricky. Is it binom.dis.range? Oh, okay. Yeah, you can use that. Telling it your first or second number. The only reason why I don't show you this because I don't expect or necessarily want you to use it because it gets a lot trickier to think about those equalities, right? So the 2 cutoff points you're telling it actually need to be. It only work if you have like strict equalities. So you can use it, and then like in this example, you would have to remember, oh yeah, I want 9 and actually not 5. I want 9 or sorry, I don't want 10 and 5. I would actually want 9 and 6 because I want to subtract. So it gets a little bit trickier to use it. So I just generally don't introduce it. Just with based off of what we do, I think it's kind of easier to set it up. Just use that binomial equation twice, and then it gets a little bit easier to think about what those cut points are, what those, we have a strict equality versus a not strict. Any other questions? We'll keep moving here. All right, so I will put this up on Canvas. So you can kind of take a look at this. This should help you with that last question on the Excel assignment. Other than that, those practice exams, try to start working through the Connect homework. You should be able to get almost all of that done. We'll talk about the Passan on Monday and then do some review Wednesday before the in-class exam next Friday. All right. Have a fun, safe weekend. I will see you guys on Monday.